So we'll go over some FRQ examples for the unit of simple harmonic motion. So the first problem we have here is we have a 10 kilogram block attached to a string with a spring constant of 200 newtons per meter. At the equilibrium point, it was originally either stretched or compressed 2 meters. And we have a 5 kilogram block being dropped on top of it while it's at its equilibrium point. So let's calculate the maximum velocity of the mass spring system before the second block is added. Okay, well we know that V max is equal to the amplitude times the rotational frequency, which is just the amplitude times the square root of k over m. Okay, and so now we just input the values. We know A is 2, and we know K is 200 over 10, so that's just 20. And this is going to be approximately 8.5 meters per second. Okay? And now that we have our original max velocity, we are now going to calculate the maximum displacement after the second block is added. What does that mean? It means we're going to find the new amplitude. So what do we start off with? Well, we'll start off with momentum because this is being dropped. Okay? So P1 is equal to P2, law of conservation of momentum. This is an inelastic collision. And so therefore it's going to be M1 V1 plus M2 V2 is equal to M1 plus M2 times the final. Okay? This is 15. This is 0 because the block is starting off at 0, right? The block is hovering over it and then it's dropped, so it's originally 0. What is the velocity of this block, though? Well, it's at its equilibrium position, so it's going to be maximum velocity, 8.5 meters per second. And we know that its mass is 10, so it's just going to be 85 plus 0 is equal to 15 velocity final. So it's just 85 divided by 15. Okay? Which is a little more than 5, around 5.67. We'll just say 5.7. 5.7 meters per second. So this is the new maximum velocity. Why? Because this is the velocity at this point, the equilibrium position, right? The velocity has gone down, and therefore, what we're going to try and figure out is what the new displacement is. So we know that this right here, so we are going to use the same formula. Vmax is equal to the amplitude times the rotational frequency. Okay? And we know that this is the same thing as A times the square root of K over M. We don't know A, but we know Vmax is 5.7 now. And then we just do 5.7 times the square root of, divided by the square root of K over M, which is just times the square root of M over K, which is just times the square root of, what's the new mass? 15 over 200. And then that gives us around 1.6 meters. So it's gone down. Why? Because the velocity has gone down. This is also, the displacement has also gone down. Alright? So that's those problems. Now let's do the second problem. So we have a not attached mass, not attached to a spring, like I said before. So it's 5 kilograms, the spring constant is 20 newtons per meter, it's been compressed 3 meters, and the distance from this frictional path with a coefficient of kinetic friction of 0.3, this one is frictionless, and that 6 meters is the distance between those two. So that means that this is also just 3 meters from it, meaning that it's going to stop once it reaches its maximum displacement, but in the opposite direction. So calculate the speed at which the block will be traveling when it leaves the spring, so at this point. So we'll mark this right here. We'll call this A, because that's part A. And we'll call this point A. Okay? And so at point A, we want to find the speed. Well, normally the speed would be 0, right? at that point, it would be 0. However, it's not exactly attached to the spring, so we need to calculate the speed. But wait, it doesn't matter, does it? Because simple harmonic motion says that it will stop here, the velocity is 0 here, and the acceleration is going to go this way. However, although it's not attached, you still have that force of the spring going this way. And because the block is not attached, it's just going to push the block to this point. So because this is 6 meters, this is just going to be 0, and this is just going to be 0, and then how far from the equilibrium point? 3 meters. So let's change this distance to 4 meters. Now that is going to be harder to answer. The last one was a trick question, but this one is going to be harder. We know that x of t is equal to the amplitude, so that's going to be 3, cosine the square root of k over m, so 20 over 5, so that's 4, so it's just 2t. Okay? And we also know that velocity in regards to time is equal to negative 3 times 2, so that's 6 sine of 2t. Like that. So what's the velocity at point A? Well, x of t, right? So at this time, we'll call time A, right? So x of ta is A, right? A. But its distance from equilibrium is 4 minus 3, so it's 1 meter. Okay? So this is equal to 1 meter. And we don't know the time, but we can solve for the time using this, right? So we can solve for the time since we know that this is 1 meter. So it's just 1 divided by 3, 1/3. So it's just 1/2 arc cosine of 1/3. That's equal to TA. Then we just plug that in here, and then we get the velocity at time A. And so what I get is time A is approximately 0.62 seconds. So when I plug that in, I get V of time A is equal to negative 5.7 meters per second. Wait a second, that's the same thing as that. Coincidence? Yeah, it's a coincidence. Because they're not actually the same. We're just rounding. This is about 5.667. This is about 5.65. They're not the same. It's just a coincidence that they look the same. Anyways, we know the velocity at this point is negative 5.7 meters per second. But the speed, it says to calculate the speed. So the speed at A is just going to be 5.7 meters per second. What was the max speed? 6. Is this the max speed? Nope, it's less than the max speed because it's 1 meter from the equilibrium position. At the equilibrium position, it's 6 meters per second. So this makes sense. That's good. So the next step is how long will it take for the block to stop and how far from equilibrium position will it have traveled. So at this point, the spring has gone back. So the spring is still actually traveling, it's just that the block is moving too fast for the spring to catch up with it. So it's left at this point. Okay? And so this is just a force problem. So we'll draw our free body diagram. And we'll do our sum of y forces and our sum of x forces. And then we'll solve for t and then delta x. Okay? So the sum of y forces is just Fn minus mg, is just the normal force minus the weight. And because it's not accelerating upwards, this is 0, and so that means that just the normal force is equal to the mass times gravity. And the mass is 5, gravity is 10, so that's just 50 newtons. Okay? X forces is just negative friction force. It's just the negative friction force. Okay? Because it's going this way, but the acceleration is this way. Right? This is the only force, but it's going that way. So it's negative friction. Okay? And so, we also know that this is the same thing as negative mu times the normal force. And the normal force is just mg, or just 50 newtons. And we know mu is 0.3, so that's 0.3 times 50, which is 15. So that means that this, which is also just ma, so ma is just equal to negative 0.3 times 50, which is negative 15. And then we divide by the mass, which is 5, so this is going to be 3. And so A is equal to negative 3 meters per second squared. So the T is just equal to, well, the first kinematic is the final velocity is equal to the initial velocity plus the acceleration times the time. So this is just the final velocity minus the initial velocity divided by the acceleration. And the final velocity is 0. The initial velocity is 5.7, so it's just negative 5.7 divided by negative 3. Approximately 1.9, because again, 5.7 is just an approximation. It's just an approximation, so that's second. So to find the distance from the equilibrium position, we just add the distance we find from point A, and then add 1 meter because we know that point A is 1 meter away from the equilibrium point. Is equal to, we'll use the third kinematic, V initial T plus 1/2 A T squared. Okay? Plug that in, we get delta X is equal to, also add 1, because add 1 meter. And then what do we get the distance is? We get 0.54 plus 1, so that's 1.54 meters. And that is it for the 2 FRQ questions.